In this next section, we're going to be looking at something called a unit circle. It's basically a circle of radius 1, and we're going to look at how the trig function values are represented on this circle. Okay, so a unit circle, again, is a circle of radius 1. It's going to be a really fun foundational discussion on trig values, because a circle of radius 1 really simplifies some of the work that we do with trig values or trig functions. Okay, so let's just draw up here real quickly a circle. We'll consider that a circle of radius 1. Remember, when you put your x and y axes on here, it forms 4 quadrants, and we've talked about the pattern in the signs of the 6 trig functions, or the 3 main ones actually. We know that all of the trig functions are positive in the first quadrant. The sine is positive along with its reciprocal, which is the cosecant, in the second quadrant. The tangent is positive in the third along with its reciprocal, the cotangent. And the cosine, along with its reciprocal, the secant, are positive in the fourth quadrant. And those are the only ones that are positive in each quadrant, okay? And so what happens then is, if you have a radius of 1, each of the points on the axes has a coordinate. Now, of course, it's centered at the origin also. They have a coordinate of either positive or negative 1, and 0 is the other coordinate. For instance, on the x-axis here, an angle of 0 degrees or 0 radians gives you a point of 1, 0. Up on the y-axis, an angle of 90 degrees or pi over 2 radians would give you, that's 0, 1. Okay, 1 in the y direction. Over here in the negative axis, it'd be negative 1, 0, and in the negative y, it would be 0, negative 1. Okay, so those aren't too bad, just to note. But what happens then is, all the points in between, they're at a radius of 1, but the x-y coordinates are obviously, they're obviously all going to be less than 1, right? Because they're either going to be to the left of the x value of 1 here, or below the y value of 1. They're also going to be to the right of negative 1 and above the negative 1 in the y direction. So all the other values are going to be somewhere between negative 1 and 1, okay, for all the points. Okay, so you have this radius equal to 1. Well, if the radius is equal to 1, remember, we developed a formula previously for the arc length of a circle. It said that the arc length S is equal to, or arc length of a sector, I should say. The arc length of a sector is equal to the radius times the angle theta, where theta is in radians. Well, of course, if your radius is 1, then you have 1 times theta, which is just theta. So S is equal to theta ultimately, right? 1 times theta is theta, 1 times anything is itself. Okay? So if S and theta are the same, then technically, if we're looking at the sine of an angle, which is generally what we do, we could actually use the arc length as the input rather than the angle when we're dealing only with a unit circle. So the sine of theta and the sine of S are the same. The sine of the angle and the sine of the arc length are the same, because the angle and the arc length are equal to each other when the radius is 1. Your textbook and my math lab will use these interchangeably now, at least when we deal with unit circle applications. When we're dealing with anything other than the unit circle, we'll be looking at the sine of theta, okay, which is more of an angle representation. Okay. What's interesting is we know that with any triangle, think about a triangle here with a right triangle. If you had an angle theta, the sine of the angle is the opposite over the hypotenuse. Okay, we typically would write that if this was on the xy axis here. You know, if I had a right triangle formed up there with angle theta at the origin, then you'd be looking at the y, the x, and the r on the triangle, right? The y value is horizontal. I'm sorry, x is horizontal, y is vertical, and the r is the hypotenuse. Then the sine being opposite over hypotenuse would be y over r. But remember, on the unit circle, r is 1. And so if r is 1, if you divide something by 1, you just get the numerator. So the sine of s is y. It's simply the y coordinate of the point on the unit circle. Similarly, the cosine of s, which would generally be x over r, is now simply the x coordinate of the point on the circle. And the tangent, I guess the tangent really doesn't change because the r doesn't show up in the tangent. So you end up with opposite over adjacent, which is y over x. But you could really think of it as dividing the two coordinates of the point on the end. It's the y value divided by the x value. Okay? So now this gives us a structure where we can identify trig functions simply off of a point, the xy coordinates of a point, and we don't even need the r value, the radius, because it's equal to 1 every time. Okay, so when we divide by it, we end up losing it. We don't really need it. Okay. What we are going to do next is we're going to focus in on the first quadrant, and we're going to look at some of the exact values of the trig functions in that quadrant, and then we're going to relate them to the other 4 quadrants. Okay, so let's take a moment here and zoom in on that first quadrant. Okay, something like that. I've got a quarter circle essentially. And we already said that the 2 intercepts here are going to be at 0, 1 for the y and 1, 0 for the x. Okay? So those are actually where the s value, we'll call it s now, oops, the s instead of the theta. It doesn't really matter, again, they're equal to each other. S is going to be, or the angle or the arc length is going to be 0 radians if it's right on the x-axis, and it's going to be 90 degrees or pi over 2 radians up here on the y-axis. Okay. Remember, to convert those angle measures, if you want to convert 90 degrees, remember you always take your angle in degrees and multiply by pi over 180, right? That's our conversion. When you do that, the 90 and 180 cancel to 1/2, so it's pi over 2, or 1/2 of pi. We'll talk, in a few minutes, we'll talk a little bit more about these conversions and the patterns we'll see in the fractions as we go around. It actually kind of works out nicely. Okay, so let's now take a look at a couple of these angles. Let's go with the 45-degree angle first. Okay, so a 45-degree angle cuts that quadrant in half essentially. 45-degree angle is a radian measure of pi over 4. It is, of course, half of pi over 2. So you think of half of a half, you get a quarter. Okay, and of course these radians can be often best understood if you kind of ignore the pi part of it. So this is like a half. This is a quarter, right? It's half of a half. The corresponding point can be found or determined using a special triangle. Remember, we looked at our 45, 45, 90 triangle in the past. And when we did that in the past, we used side lengths of 1, 1, and root 2, right? If this is a 45, 45, 90 triangle. Well, pi over 4 angle or 45-degree angle are the same. But now I don't have root 2 as my hypotenuse. I actually have 1 as my hypotenuse, right? So how would I change root 2 to be 1? Well, I would have to divide by itself. I'd have to divide it by root 2. If I divide that by root 2 to make the hypotenuse 1, I've got to scale all the sides the same way. And so I'd have to divide everything by root 2, okay? Well, of course, when we divide by a square root, we've got to rationalize the denominator. To rationalize denominators, we've talked about this before as well. You multiply the top and bottom. Cap won't come off. You multiply top and bottom by that denominator. So multiply by root 2 over root 2. Do the same here. Of course, we're going to get the same value because the two sides, this is an isosceles triangle, so it'll be the same. And when we multiply by that, we end up with root 2 over 2. Okay, square root of 2 over 2. And so those are going to be the corresponding x and y values of our point. Okay, so it's going to be square root of 2 over 2, square root of 2 over 2. Those are the xy coordinates of the point at 45 degrees on the unit circle. So it's this point right here on the unit circle. Okay, you can always check these two. Remember that if you wanted to check them, you could put these into the Pythagorean theorem, square one of them, square the other one, add those squares together, and it should equal the square of the hypotenuse, which we know 1 squared is 1. So if we square this, add them together, you should get 1. Okay, and you would if you did that. Okay, so that's the first one. The next one we have to look at is the 30, 60, 90 triangle. I'm going to erase a little bit here. Give myself a little more space. Okay, so let's look at the (30, 60, and 90 triangle. All right, so with this one, we know that in the past we've seen the side lengths to be 1 on the short leg, 2 on the hypotenuse, and square root of 3 on the longer leg. Well, again, the hypotenuse on a 30, 60, 90, we'll kind of run this up on a 60-degree angle here. We could also run it on a 30-degree angle. We'll focus on the 60 for a second, and then we'll kind of switch everything around and look at the 30, because it's kind of how I have it drawn. So we know the hypotenuse is not 2 on this circle, it's actually 1, right? So I need to divide this down so that it's a length of 1. Shrink the triangle to a similar triangle, I should say. And so to do that, we're going to divide by itself, right? 2 divided by 2 will make a hypotenuse of 1. But again, if I shrink one side down, I've got to shrink all of them down by the same factor. So I've got to divide everything by 2. That shrinks the whole triangle consistently so that we have a similar triangle, still a 30, 60, 90. This one works out very nicely. I don't have to rationalize the denominator like we did before. Everything is already rationalized. And so we have an x and a y value for this angle. Now remember, a 60-degree angle is pi over 3 radians. Okay. And remember, a 30-degree angle is pi over 6 radians. So remember that relationship. That is going to become very important. Pi over 6 and pi over 3, that they are, the 6 and the 3 switch. Remember, the 30 degrees has the 6, and the 60 degrees has the 3. So with a pi over 3, that's a 60 degree angle, the x coordinate is 1/2, the y coordinate is square root of 3 over 2. Okay, so we have 1/2, comma, square root of 3 over 2. Again, x and y are the horizontal and vertical sides respectively. Now if we rotate this triangle around so that we're looking at a 30 degree or pi over 6 angle, or arc length in this case, well, all you really are doing is, if you put the 30 degree on the bottom right now, we still have, I'm going to rewrite this with the scaled factor simplified, so we have a 1 radius, the x becomes the y and the y becomes the x. That's all that really happens. So we'd have 1/2 and root 3 over 2. And so all I do is I take the two coordinates here from the 60 degree angle or from the pi over 3 and interchange them. So the x becomes the y and the y becomes the x. So I have root 3 over 2 and 1 over 2 for the y. Okay? Okay. That's really all that we can determine with exact values at this point. All the other angles in here and all the other points on the circle will be determined in other ways. In fact, we won't really be able to get to a whole lot of these. Your calculator can. And so we will discuss a lot of them on the calculator or be able to find them on the calculator. These are the only 3 that we can really determine, actually 5 I guess with the 2 axes, that we can determine by hand exactly, okay, with some sort of exact value. All the other ones really require some sort of approximation technique, which again your calculator does, but you wouldn't be able to really do that without some like calculus knowledge. Or there are some things when we get into, I think, chapter 5, we're going to see some formulas that we're going to be able to use to get some of the other angles in here, like the 15 degree angle and the 75 degree angle, some of those. So we will see some of these show up, but not a lot. Okay, some of the other ones. Okay. So again, this is very useful because now I can calculate my sine, cosine, tangent of these angles using simply the x or y coordinate, or both, of the point on the unit circle at that angle. So if we take a look at that for a moment, let's get rid of some of this. So I know now that the sine of s equals y. So if I want the sine of pi over 6, and I understand the unit circle here, I know that it's the y coordinate of that point. It's just 1/2. Okay? If I want the cosine of, let's say, pi over 4, well, the cosine of any arc length here is the x value of the corresponding point. So pi over 4, the x value is square root of 2 over 2. Okay. Now, what's also interesting is that we can get trig values or trig function values at the axes, where you don't really technically have a triangle there, right? If the angle is 0, you're not really looking at a triangle, it's only one-sided. You can almost think of it as the y, the vertical side, shrunk to 0, and the horizontal side and the hypotenuse are the same, okay? And so we could even calculate some trig values on the axes. Not too bad, just by using the 1 or the 0, the x and the y. So for instance, the sine of 0, right, is 0 angle or 0 arc length. The sine is the y value, so it's equal to 0. And the cosine of 0 is equal to 1. Okay, that's the x value. The tangent, I said tangent, I wrote sine. The tangent of 0 is equal to the y over x, 0 over 1, which simplifies obviously to 0. Okay, so So we can now start to look at trig functions that don't really have a specific triangle associated with them. So if I want to do the pi over 2 angle, or pi over 2 arc length here, we could do the sine of pi over 2 is now, sine is the y value, so that would be 1. And the cosine of pi over 2 is equal to the x value, which is 0. And the tangent of pi over 2 is the ratio of y over x, so it's 1 over 0. Well, remember 1 over 0, anything divided by 0 is undefined. Okay, so this isn't actually a value, it's actually undefined. There is no tangent of pi over 2. Okay, it's an undefined value. Actually, it is no value. But now using these, we can also find the reciprocals, the cosecant, the secant, the cosecant, and the cotangent at each of these values as well. What you'll see is a lot of them end up being undefined as well, just like the tangent was, because we end up with zeros in the denominator. For instance, if I wanted the, I have a habit of writing cosecant as COS, but it's not. Cosecant is CSC of 0. The cosecant of 0, remember, is the reciprocal of the sine. It would then be 1 over 0, and 1 over 0, again, the 0 is on the bottom, which makes it undefined. Okay? The secant of 0 is the reciprocal of 1. Well, the reciprocal of 1 is 1, right? So 1 over 1, equals 1. And the cotangent of 0 is the reciprocal of the tangent. So it's 1 over 0, right? The tangent was 0. And that, of course, 0 is on the bottom, is undefined. Okay? So we are going to have some undefined values showing up in there. One thing that I want to really point out is I'll stop. We're going to go to another video here in a moment, but just to lead into that is I want to start looking at some limitations on the values of sine, cosine, tangent, and their reciprocals, and then kind of looking at some patterns in the fractions as we sort of rotate this into the other 3 quadrants.